homogeneous differential equations, and I don't know how much. And we can look at this simple example here. Okay, so basically before we impose the physical things, I want to start from here, from the very beginning, the differential dFEQ. Okay, so maybe we can use this example to demonstrate. And I like to keep this in the big pictures here, and we work on here. So usually for this simple example, I just make it up, okay? And I just make it up, and you see this is a typical, this is a differential equation with a constant coefficients. But in terms of our vibration, you can see this is a system with m equal to 1 and 2 zeta omega. So you can see this is a very typical standard vibration systems, okay? And this one is new to us, and this term in our chapter 2, this term is equal to 0. We call the free response. Okay, but right now we're considering here is the harmonic excitation. Basically, this is one example of this. So again, harmonic excitation can be sine or can be cosine of the single frequency. So for this case, we are given the initial conditions, and then we want to solve for this one. In terms of differential equations, we know this is called the non-homogeneous differential equations because this term is non-zero. Okay, so again, for non-homogeneous differential equations, then we know the solution must have two parts. One is called the homogeneous part, homogeneous solution. The other one is called the particular solutions or non-homogeneous solutions, depends on the textual terminologies here. Okay, so that's the definition here. And how to solve for this? So basically here the x of h is what we have learned. So x of h is solved by solving the homogeneous portion of the ODE. Okay, so this is called the homogeneous portion of the ODE, homogeneous solution. Homogeneous portion, that means this term equal to 0. Okay, and what is these solutions here? And we know that is our part of the chapter 2 exercise, right? So for this case, right now you can see the root, the characteristic root is how much? Equal to 2a minus b. So that's the root. Okay. So in this way, the x of h will be equal to, under this case, you should be able to write it. What is that? It's a couple form, right? And I like it in the form, the capital X. I like this one. Okay, or otherwise that can be in the combination is say C1 exponent minus 1 plus 2j and plus C2 exponent minus 1 minus 2j, right? Because if you remember, again, if we have two roots, say if we have two roots equal to P1, P2, then the homogeneous solution is the C1 exponent P1t plus C2 exponent P2t, right? So that's the generic patterns we learned before. Okay? So basically, simply I want to describe is what we have learned in chapter 4 is to get ourselves ready for these portions. Okay, so this one right now, assume we can just move on. Okay, this is a quick review. And right now so right now this one is determined, and basically we know the C1 and C2 or X and V are determined by the initial conditions. We've been exercised quite a bit through the homework before and the test, right? Okay. Will feel good about this portion? Good? Okay. So now our focus is on this portion today. And for this exercise, this one XP is obtained by solving the entire equations. Okay, XPT must be the solution to satisfy this one. And when we learn differential equations, actually we have learned quite a bit these I would say procedures for corresponding to different forms of the non-homogeneous part. And this such as trigonometry, and the sine cosine is the simplest form, right? So, and we have other many types. In particular, for such this form, then we know that when we want to set it up, the information ready to go to solve for is this. Here I'm going to directly pick up the result from there. Because this form is in trigonometry in the sinusoidal functions of sine. So for the XPT, we can assume that is in the sine t. Okay, the same patterns. Okay, but in addition to this form, because we know sine and cosine, basically when sine take a derivative of sine become cosine and vice versa. So we might want to make a guess of the assumed solutions that is complete. Complete, that means we won't miss any piece of the information there. So once you see there's a sine appear, you must also take its counterpart cosine as well. I think that is a tip being taught there. And that should be in combination of the two terms here. So let me say this is alpha and beta. And we don't know the combination coefficients alpha beta, and that is the process of going to solve for. This is a very important. This is the most important step. We assumed the solutions, and with the assumed solution, we try to solve for the unknown things. And if at the very beginning, if the assumed solution form is not correct, then basically that affects all the remaining result, right? Okay, so hopefully you can gradually have some kind of piece of information from DBQ coming back here now, okay? So here we assume the solution is like this, and we're going to solve for alpha and beta. Be okay? So in this way, because here we have a double dot, we have dots, so simply we get a derivative here, xt dot, and that one will be, here I try to arrange the alpha beta in the same column, so sine take the derivative become cosine, and alpha, and cosine take the derivative become minus sine. Okay? And then we take the double derivative. So this one, sine become cosine, so that is minus beta, cosine t. And cosine becomes sine, minus sine. Okay? Okay. So right now we can see, and basically this is in combination of the coefficients. So here let me multiply the coefficient. This coefficient is 1, and this coefficient is 2, and this coefficient is 5. So simply we take those one, we sum them up together. Okay. So on the left hand side, that is x double dot and plus 2x and plus 5. Okay. So on the right hand side, we can take it. So I'm going to write down very low here, and probably need to stand up. So that is alpha minus alpha, and that, let me stand up here, alpha minus beta minus alpha, and sine t plus beta plus alpha minus beta. Am I right? I made a mistake. Because I need to multiply with the corresponding coefficients. Okay. So for this term, multiply with 5, so that is 5 alpha. And the second term, multiply with 2, so minus 2 beta. The third one is 1, so that is minus alpha and sine t. Okay, and this one is 5 beta, and then plus 2 alpha and minus beta cosine t. Okay, so that's the result. And again, from our original, that should be equal to 2 sine.
Question.
Yes, go ahead.
Should that be minus cosine t? Here, there, or to the right? To the right.
Yep.
To right after the sine t. Should that? should the 5 beta plus 2 alpha minus beta times cosine of t be negative? Should this be a negative number?
Go ahead.
Should this be positive?
Yes. Thank you. Yeah, good. Okay, so you know what I'm doing. You know what you're doing. Okay. So under this case, and that original, so we have this one. So simply from here you can see this one, we simply compare term by term. For sine t, that means compared to the coefficient of the sine term, so that means this term must be equal to 2. So let me write it down here. So that means 5 alpha minus 2 beta minus alpha equal to 2. Right? And then we compare to this one, the coefficient of the cosine equal to this, and that is nothing. So that coefficient of the cosine must be equal to 0. Will be okay? So that is the coefficient of the sine t. This is the coefficient of the cosine t. You good? Okay. So from here we can solve for alpha equal to 2 over 3, and beta equal to 1 over 3. So based upon our understanding and review of the differential equations, we assume this form. And then we solve for this one. So therefore, the total solution. The total solution is the homogeneous solutions plus the particular or steady state solutions. And this one, basically, we write it up together. And that will be equal to let me pick up this one. So again, these portions is our X, the homogeneous solution. That is our topic from chapter 2. And this portion is our particular solution, and that simply is a little bit new stuff from our topic this time. Okay. So for this one, right now, how many unknowns we have? Two, right? And what is the unknown? So from here, you can tell the unknown is capital X and capital Phi. Okay. To solve the two unknowns, right now we haven't used up our initial conditions yet. So we can use up our initial conditions, apply the initial conditions to the total solutions. Okay. Not when we learned chapter 2, we applied the initial conditions to the homogeneous solution only, because back to them we don't have any force vibrations. So now I want to tell you the third important note. When we solve for the total response, we apply the initial conditions to the total response. Okay? Not to this portion, not to homogeneous only, to the total. You good? Okay. And from these portions, I think I'd like to write up this form, but this form, you know, from our exercise of the homework, seems it's not so easy, so straightforward to solve for. So right now, I think this portion I can write it up is like this: ET and say C1. Let me use the say A1 sine 2t plus B AB cosine 2t. E to minus t, yes, thank you. Okay. So basically we know this one simply is in combination cosine and sine. So maybe we can write it up in this form, and solve for AB will be a little bit more straightforward. Or otherwise, we have an exercise in homework. We know how to solve for the X phi in terms of this one. So basically that is kind of up to you. Okay, really up to you which form you like. Okay, so under these situations, then either way. So we introduce, so the next step is to introduce the initial conditions. Into X total. To solve the two unknowns. Unknowns, that means capital X, B, or A, B, depends on which form you like. Okay? So the result, let me get that result. So let me write it up here. So in this way, we can get the total response equal to exponents minus t and minus 3 cosine 2t plus minus. Okay. I think that is the things here. So in these portions, this one is our X of H, the homogeneous solutions, and these portions is our particular solutions. So you see in our solution process, we divide. So this is a process for homogeneous solution. That is a process for particular, because this is a linear system. We can solve for the two portions separately and then superpose together. Okay. So right now I want to talk about a little bit more about the features of the solutions, and that is my duty to give you such explanations. Okay, and those one are, I would say, old stuff. Suppose you can get it from your DBQ. Okay, and more importantly is how can we gain insight into the solutions, the mathematics expression behind. So for the particular solution for this example, you can see right now. Let me draw it. We can look at the graph of the response. Okay, so this is the response. Okay, response, and I'm going to draw it. So using the blue line to represent the homogeneous solutions, and that response can be something like this. Okay, and I started from negative because by looking at these coefficients, I know a little bit more detail, and they should be from negative. Okay, but otherwise, generically, schematically, we can start from anywhere. So that response is something like this, and the frequencies, from here to here, the peak to peak, the period simply is 2 pi divided by the frequency is 2, so the period is equal to pi, right? So the time is in seconds. Okay. And for homogeneous solutions, and that is the green part, and that should be something like this. So basically, if really we want to do it, then let me try to draw it. So this one have the coefficients. Say this one simply we want to do more. We can combine with is 3. Okay, something like this form. We can calculate the phase angle, but the magnitude is about that big. Do you know how to do this? The magnitude simply equal to the square root of the coefficient of this 2, 3 square plus 1, 3 square. Okay, so that is at this one. And taking the tangent of something, then we can calculate this one. Again, go back to our homework. Okay. So right now this is our form. So taking that one magnitude and then something like this. Okay, let me try to draw it in a good way. 1 cycle, 2 cycle. Compared to our homogeneous solutions, for this particular example, the working frequency, this is of the t, right? So that means from here, the period equal to 2 pi divided by its frequency equal to 1. So basically, the period is doubles of the homogeneous solutions. Okay, when we want to draw it, we can draw it. So the total response can be numerically, can be point-wide, the summation of the two curves at the particular positions. We simply superpose together. But here you can see, for these systems, because the system has a damping, that can be obtained by looking at this term here. That tells us the damping, right? So we know the system response, particularly the homogeneous response, is going to decay. So once we superpose the solutions together, you can see when time goes by in the long term, the system's response will be totally governed by the green curve. Will I be right? Good? Again, the system's response eventually the system eventual response will be totally governed by the green curve. The green curve is the total is a particular response. So eventually, the system response we call the steady state. In more kind of scientific term, the eventual we could define as a steady state. Okay, so the reason why we say that is a steady state response. The system's response eventually is governed by the green one. So that can be explained of this kind of form from here very clearly. You good? Okay, so I think if you can download.